So I'm having more, much to my dismay, having more Spotify API issues. So if I don't stop at 3:48, just wave me down and be like, hey, you have to stop now. I'll still stop at 3:48. I'll try to keep an eye on the clock, but it's saying for anyone interested or anyone possibly seeing the same issue or sees the same issue in the future, I'm getting too many requests for my response. So it's saying I'm hitting the API limit, which there's no way I'm hitting the API limit. The API limit's like hundreds of requests a minute or something like that. There's a 0% chance that I'm hitting that. So I don't know why I'm being cut off by the API. It's not something in my code. Maybe I left my script running and it hit a loop and sent a bunch of requests. It's possible, but the cooldown should have been over by now. So let's do this. So the music's not going to start automatically, is the point to that. So we want to continue our conversation about WebSockets. Last time we talked about the WebSocket handshake and how that's going to establish the WebSocket connection, which, great, but establishing the connection is pointless if we're not going to do anything with it. So today we want to talk about how we're going to send messages over this WebSocket connection. That's the big thing we want to talk about today. Oh, I didn't do Big Mouse today. Might get away without doing it at all today. All right, so WebSockets. We established the connection. I already said that. We established the connection. Let's send messages over this WebSocket connection, which really is just a TCP connection. So how we're going to do that is like this. I could, if I was much grumpier and didn't feel like doing anything, I could just say, here it is. Go read the RFC, and that's how messages are sent. Of course, I'm not going to do that. I'm going to go through slides and explain it. And then on Wednesday, we're going to do testing, and I'm going to run my server and show you sample frames and all this stuff. We're going to talk about it a lot. But really, this is it. This is it. And then reading the RFC to get this RFC 6455 to see the exact specification of how everything is. That's the ground truth for everything, in this case for WebSockets. The RFC, as always, I haven't mentioned this in lecture for a while, but the RFC is always the ground truth. That is the protocol. Everybody starts with RFC 6455 to understand what WebSockets are. The handshake is in there. The frames, this format's in there. Anything else you want to know about WebSockets is in that RFC. The people who write browsers read the RFC. The people who write servers read the RFC. Everybody complies to the RFC, and then WebSockets happens. That's how a protocol works. We have some ground truth of what the protocol is. Everybody follows that, and then we can have communication over the internet effectively, which is pretty neat. And this defines what order the values are going to be, specifically what each bit means. We can just send ones and zeros over the internet. So what do those ones and zeros mean? What do they mean? The protocol decides what they mean. This is what they mean right here. We've seen this already. Oh, I got ahead of my slides again. I'm just so excited to talk about WebSockets. So I actually am. I like WebSockets. The protocol is going to specify what those ones and zeros mean. And we have seen this twice already. I very briefly showed these two images for IP and TCP. We're never going to have to mess with these in this class. You take modern networking concepts, you'll understand a lot more about what these actually encode. But all this is saying is when we send ones and zeros over the wire, it's going to be in an internet packet. So we have to have these headers. The routers are going to read these headers to figure out where this packet is going. Once that packet gets there, the specific machine is going to read the TCP headers to figure out which, among other things, which process to send this message to, doing the sequence numbers, piecing together one message that's across multiple internet packets, and then sending that to the correct process that's listening on that port. Your web server is listening on port 8080. Your operating system's going to do all the TCP, reassemble the packets, and then send that overall message after the entire message has arrived, send that message to the process listening on port 8080 and say, hey, I got some information for you. It came from this IP and port. Here's your message. Put it on your buffer, and then you call receive, and you actually get the content of the TCP request. So all of this is handled by your network and by your machine And then once you get to to your process, the application level layer, if you studied network before, the application layer, that's where we care. That's where it's HTTP. That's where it's WebSockets. In this class, we care. So finally, we get to use one of these things. HTTP is all, as we know by now, it's text parsing for the headers, and then the body can be whatever. But WebSockets is going to follow the structure more closely following the TCP and IP protocols. It's going to follow that structure where it says, this is what each bit means. These are all the bits. You're going to get a message. You're going to read the bytes. You're going to separate those into bits, and this is what each one means. Same thing that the routers are doing, same thing your operating system's doing for TCP and IP. Respectively, I did those backwards because we always like to say TCP IP. I still feel like it should be IP TCP because it seems like it's in the right order. I don't know. Maybe some people think TCP IP rolls off the tongue better. Kind of does. But that's what our protocols are. So when a WebSocket packet is flying through the internet, it's actually going to look like this. You're going to have those IP headers, the TCP headers, and then the WebSocket headers, and then finally the actual payload of that message. But all these headers are going to be stacked on top of each other. So when a packet's flying through the internet, we're going to read the bits and figure out what all these values are, or rather for IP, the routers are going to figure out what all these values are. Most importantly, source address, where's this thing going? So it can figure out where to send that packet. And then the next step at your machine, it's going to read all these headers, figure out what sequence number to put these together, and then destination port, going to be the two big ones here, to figure out how to piece this message together and then send it to the right port. And then we get it on this port after all these headers have been stripped off. The IP and TCP headers are gone by the time we get them. We don't care what those headers said. Those headers are mostly meant just to get the information to us. And then once we get the message, our first byte is going to be right here. So more of a zoom out, a reminder of where we're at in the whole grand scheme of the internet. This is where we're at. We have 3 protocols in our network stack that we're concerned about. There's more. There's the transport layer, like Wi-Fi and Ethernet. But these are the ones that we're concerned about, but mostly WebSockets. That's what we're concerned about right now. Yeah. When the bits count up to 9 instead of 7? I'm not quite sure what you mean. They on the top here. I almost hit the wrong button. The second line. Wait for WebSockets. Yeah. So this is. I don't know why they do this. I wish they would do this a little different to avoid this question. There should be zeros up here and then ones up here. But it's saying 0 through 9 and then 10, 11, 12, 13, 14, 20, 21, 22, 30, 31. So this is 32 bits wide, 0 through 31. So we have 4 bytes wide of the protocol. And that's all visualization. Of course, it's one solid stream of bytes, but we think of them 4 bytes wide as humans when we're looking at the protocol. Makes it easier to visualize. But yeah, if they just put the extra 9 zeros and the extra 9 ones and 2s and the extra 3, it'd be a lot more clear what's going on. Okay, so the situation we find ourselves in is we have to parse at the bit level. We started at strings, we moved on to bytes. We're at the bit level. How do we parse in bits? And we got to parse this and get all the information out. So what I want to talk about mostly today, for probably the rest of the day, I should take up the whole lecture, is hopefully we finish by the end of the lecture, is figuring out what every single one of these means. What does all of this information mean? So let's go through it. And in your code, I'll start off by talking about in the code, you're used to receiving the bytes. You already have a byte array. Every time you call receive, it's returning a byte array. And you can get specific indices of that. So you can get the first byte, for example. If you get the first byte out of a WebSocket frame, you're going to get the first 8 bits. You're going to get this fin bit, 3 reserve bits, and an opcode in the first byte. And that's going to be an 8-bit integer value, which is usually, if you print that to the screen, depending on a lot of factors, you're either going to get a number from 0 to 255, or I think Python likes to give you the ASCII equivalent, so you'll get the actual ASCII value. I forget what situation is which. But I like to manually convert it to whatever I want. Then I don't have to think about the default, whatever the default is. And then you'll work with those 8-bit integer values, which is what a byte is. But just remembering that they're usually ints, but they're also bits. And we have to treat them as both at some points in this code. For your test, for test 2, of course, we're in Learning Objective 2 in homework 3. I call them homeworks here and tasks in 116. I always get mixed up of which is which. I should just normalize all my naming across all my courses. So we have to parse bits. How do we parse bits, you might ask? I'm glad you asked. So here's where we have to think about our binary operators and what they are in code, which possibly you might never have used before. I wouldn't be surprised if you haven't, if this is the first application where you actually have to think about, actually have to use this in code. But we're going to use the bitwise AND operator as a bit mask. So for example, if I want to extract the opcode out of the first byte, this first byte is going to be some value from 0 to 255. It's going to be an 8-bit integer. And if I AND that, a bitwise AND, which is ampersand, if you ever wondered why our logical AND is ampersand ampersand and not just one ampersand, is because a single ampersand is a bitwise AND operation. And we needed bitwise operations first, then we needed the logical ones, and people were like, oh, I don't know, let's just slap another ampersand on there. I imagine how the conversation went. But the bitwise operators are more fundamental to the computer. Those ones definitely came first. The first processor anybody wrote needs bitwise operations. So single ampersand is our bitwise AND, not our logical AND. So if I have the task of extracting this opcode, I can use a bit mask of 15, take my integer from 0 to 255, and it, bitwise AND it with 15, which is 00001111, and that's going to effectively zero out the first 4 bits of this byte. It's going to return a value from 0 to 15. It's either all zeros or all ones, or anywhere in between. With all the higher order bits, the 4 higher order bits, always being 0 because we ANDed them. 0 and anything is 0. 1 and anything is whatever the anything was. So what we're left with was whatever those 4 least significant bits were before the bitwise AND. So we're effectively masking for the 4 lower order bits using a bitwise AND and getting just the opcode extracted from this byte. Gives us a value from 0 to 15, and then whatever opcode we're looking for, we can say if this opcode is whatever, do this. If it's this, do this. We can change our operation based on the opcode. All right, so that's bitwise. And then, of course, this applies through, if I want the payload length, I'm going to do 0 and then 7 ones to get the payload length. A 1 and 7 zeros if I want the mask, so forth. But bitwise ANDing to mask out the values you're interested in is the key there. Yeah?
Why aren't we not shifting for, obviously 0, 0, 0, 1, 1. Why aren't we also left shifting for after that?
We wouldn't. We wouldn't want to. No, but I know what you're saying here. So, for example, if I wanted just the fin bit, I can mask it with 1 and then 7 zeros, which should be 128. 128 if I'm remembering right. And then you can shift right. 7 positions, and then if it's 1, the fin bit was 1. If it's 0, the fin bit was 0. Or in that situation, you could just shift right by 7 bits, flat out. You know it's an 8-bit integer to start with, so you're not worried about massing out some higher order bits here. You know this is the highest order bit. You could bit shift right 7 positions, and that's your fin bit. You get there all in one shot. A logical shift left and right is 2 arrows in our code. 2 greater than signs or 2 less than signs, and the arrows point the way that you're shifting. And then an integer. So if I do my byte, right arrow, so greater than, and then 7, that's going to shift right 7 bits, which can also be useful in this homework. Yeah.
Are we guaranteed when shifting left or right what shifts in? Like I know if it's shifting left, you might shift in a 1 or 0 depending on the platform. Do we know what it would be?
In Python, I don't think you, with their languages you have that issue, platforms you have that issue.
Yeah.
Would C just give you whatever random garbage was over there?
0, but in 220 they made sure that you knew that there would be an issue depending on the platform you're working on. Because if you want to
Yeah, because that sounds like a C thing. You do bitwise operations in 220? Oh man, I should know that. Okay, so this isn't the first time you do bitwise in code. Oh, that's good to know. I don't have to build it up so much then. I got to look into that. What exactly you do there? I feel like I should know that. All right. Yeah, that's good. You're used to this then. you all got this. This is easy. All right, so that means I can cap that conversation and just talk about what all these bits mean. So the fin bit, this is either going to be 1 if this is the last frame for a message, or 0 if this is a continuation frame. Last semester, and possibly next semester also, I would have continuation frames, and this would sometimes be 0. For this semester, this is always going to be 1. Every message is going to be a single frame. You're not going to have to deal with multi-frame messages, which, again, it's to limit the difficulty a little bit, just like we're, forget what I'm limiting on image uploads. Oh, yeah, I don't have a second piece of information in the form. The form is just the image. So a few things. We'll see if you all do really well. If you want to see next semester suffer, do really well on homework 3, and then I can add all those things back in for next semester. And then they'll suffer. They'll have to do all the stuff. But this bit is always going to be 1 for our purposes. You can make that assumption in your homework. I'm fine with that. You assume fin bit's always 1. Reserve bits, the next 3 bits are reserved for extra operations. Some protocols that add on top of WebSockets might use these reserve bits for special purposes. We're not in the homework. We're using just straight up WebSockets, just the fundamental protocol. We're not going to add any extra functionality to it. So all the reserved bits are always going to be 0 for our purposes for the homework, and we never have to check those. It's to make the protocol extensible in the future and for other additional protocols, not using them, which I don't know. So reserve bits. So the first 4 bits, you can already assume what they're going to be. They're going to be 1, 0, 0, 0. So no real need to check those ones. If you don't feel so inclined, just check them. Next is the op code or operation code. This we do have to check. This is the first one we have to check. Not for straight zeros. That's going to be a continuation frame. If the fin bit is 1 or 0, you can have either case. The last frame of a message will have a fin bit of 1 and an opcode of 4 zeros. Again, not worrying about that this semester. But you will have to handle either 0001 or 1000 for either text message. All of our messages over WebSocket frames are text. This is what we're replacing Ajax and polling in the chat with. We're replacing that with WebSockets. So it's all going to be text, just chat. We could send binary if we were so inclined. We're not for the homework. That I never had students do. If you can do text, you can do binary. It's just extra work without extra understanding. Continuation frames is actually an extra feature that you have to build, though. But text, or it's going to be a 1000 for a close operation. This is when the client closes the WebSocket connection. If you get a frame that says this is a close opcode, you do have to handle that gracefully. And this is in the testing procedures. We're going to open a tab and then close a tab. send a message or two, close the tab. That's going to send the close opcode to your server, and you have to gracefully shut that down without having all kinds of errors and crashes in your server. So a close or text is going to be one or the other. This is binary, so this is either 1 or 8. If you're treating these as ints, you might have somewhere in your code, if opcode equal 8, then do this. Or if you want to do the binary thing, you can check if it's the bits 1000, 100. Oh yeah, that was the right number of zeros, right? 1 and 3 zeros. Next is the mask bit. This is either 1 or 0 based on whether or not there is a mask. So we have the mask bit, and then the masking key, which is a 4-byte value later in the frame. If the mask bit is 1, then the masking key exists, and you have to handle that masking key, which we'll talk about later. If the mask bit is 0, then this masking key does not exist. So that means these 4 bytes in the protocol just are not even there. We go right from payload, all this payload length stuff that we're going to talk about at length, and it's going to take a lot of coding. After all this stuff, it goes right into the payload and skips the masking key if the mask bit is 0. So the mask bit tells you whether that key is there or not. This will always be 1 when you're receiving a frame. When you're getting a frame from the client, mask bit will be 1. When you're sending a frame to the client, your mask bit will always be 0, and you're not going to have a masking key in the frames you send. So the frames you receive and the frames you send, they'll follow the exact same protocol, but you're going to set the mask bit to 0, and the client's going to set that mask bit to 1. So there will or will not be a masking key, depending on whether you're receiving or sending these frames. It will always, 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 always be 1 when you're receiving a message from a browser. I shouldn't say that many always. I mean, maybe there's some browser with a bug in it somewhere, but it should always be 1 when you're getting a message from a browser. It should always be 0 when any server is sending a message back to a browser or back to any client. And then the payload length. Oh boy, the payload length. Let's talk about it. Let me catch up on chat first. So we got chat. That was from earlier. For opcode, is it always doing bitwise with 15, or does it change? Last week you said that the bit mask is random, so I'm a little bit confused. This masking key is always going to be random. This is going to be a different value every single time you get a frame. Even from the same client, it will regenerate a new masking key every single time, completely random. That's what I meant by the key being random, or the mask being random last time. The bit mask that you use for the opcode is always going to be 15 because you specifically want these bits. So you need those bits to be 1 in your masking key. So it's a little bit overuse of the word masking key. Did I say masking key even? Yeah, I did. So it's an overload of the masking key, that word. But the masking key here and the mask that we're using to mask out those bits, it's just overuse of the word. 2 different uses of the same word. Okay, the payload length. Let's talk about this. The payload length is very similar to content length. It tells you how many bytes are in the payload. So we have the payload, the actual data we're interested in down here. Payload length tells us how many bytes are in this payload. Just like content length, and it serves the same purpose, something we'll talk about at length on Friday. It serves the purpose of letting us know when we're done reading bytes from the TCP socket. So we need to read this many bytes. We're going to go to our TCP socket and keep reading bytes until we read that many bytes, and exactly that many bytes, and then we're going to stop reading bytes, process that message, and if we read too many bytes, we know that the extra ones are part of the next WebSocket frame. So it's doing quite a bit of work for us, this payload length and content length. Both of those, we're going to talk about them on Friday with buffering. How do we make sure we read exactly that many bytes? So computing the payload length is what we want to focus on today. And the payload length can either be represented as 7 bits, 16 bits, or 2 bytes, or 64 bits, or 8 bytes. These are the 3 kind of modes for the payload length. if the payload length, so we have 3 different situations, and you should have an if, else somewhere in your code that's going to check for these 3 modes of payload length. And when you send frames, making sure you get the right payload length in the right format based on which one of these 3 modes it should be. If the payload length is less than 126 bytes, then the payload length is represented in 7 bits. It's going to be right here. The payload length is just this, and that's it. And then the next byte is going to be either the first byte of the masking key, if the mask bit is 1, or the first byte of the payload, if the masking key is 0. All the rest of this stuff doesn't exist in that WebSocket frame. Which is kind of beautiful. This is as good a time as any to appreciate what the WebSocket protocol is doing for us. We're stripping everything down right to the TCP socket. And this format is exceptionally minimal that we have such little overhead on each message. Something we should be concerned about if we're concerned about efficiency is how much overhead is involved in sending a single message. To send one HTTP message, we have to have a TCP 3-way handshake. We have to have a key exchange if it's HTTPS. So we have a lot of back and forth on the network. Then send a request, get a response, and then for what we're doing, we sever that connection immediately. We can use the keep alive and use the same TCP connection for multiple messages, but then we still have the overhead of HTTP headers to think about for every single message. With a WebSocket connection, we're reusing the same connection by default with no extra work because that's just how WebSockets work. We're going to keep that TCP connection open, and we have, if we have less than 126 bytes that we want to send, we have 1, 2, and then if it's from the client, we have a masking key, 3, 4, 5, 6 bytes of overhead. 6 bytes of overhead. That is almost 0. That is so ridiculously small. For comparison, if you're sending an HTTP request in 6 bytes, you can't even specify the HTTP version. That's going to take 7 bytes just to put HTTP/1.1. You're already over what one WebSocket frame overhead is, and that's not talking about the path, the method type, all your headers. You're going all your blank lines and /r/n's. Every /r/n is 2 bytes. Just to have your new line characters, you're going to have 6 bytes with 0 headers, or with 1 header, I should say, with 1 header, and then 8 bytes. Anyway, there's a lot of overhead with an HTTP message. A lot of times we're not too concerned, but if you have WebSockets, the goal is to have live communication. You want your messages getting there as fast as possible, as minimal processing time, very fast, and boy, does this protocol get there. That's such little overhead, and it's built right on top of a TCP socket. We don't have anything else other than network stuff as overhead. Very, very optimal. Very efficient. If you want to send more data, so if you have more than 126 bytes but less than 64K, then we're going to take 2 extra bytes, still just 2 extra bytes of overhead. Most of the content is your actual, most of the message size is your actual content. If you're in between these 2 values, then this 7-bit payload length is going to be exactly 126. Exactly 126, and then the next 2 bytes are your extended payload length. These 2 bytes right here will exist in this case, and then that will be your actual payload length. So the 126 7-bit payload length is your indicator that the next 2 bytes is your actual payload length. So whoever, the designers of this protocol really wanted to save every single byte. If your message is less than 126, we're not even wasting extra bytes to represent the payload length. Or else they would just say, payload length is always 8 bytes or something. They were worried about saving those extra few bytes of data. So if this is 126, then you got 2 bytes is your payload length. And then the next byte right here would either be masking key if there's a mask, if you're receiving this frame, or if you're sending the frame, this would be your first byte of payload. In sending a frame, you would only have 4 bytes of overhead to send up to 64K bytes of data. Very, very little overhead. If your payload length is more than 64K, then the payload length is going to be exactly 127, and the next 8 bytes are going to be your actual payload length. 64 bits to represent the payload length, which means your payload length in a single WebSocket frame can be up to this number, which is about 16 exabytes of information, which I think, they must have been thinking of the IPv4 to IPv6, like we ran out of IP addresses. They must have been thinking along those lines and saying, bless you, and saying, man, we really don't want to run out of space here. And even with this, even with the max frame size being 16-ish exabytes, or 16 exactly, right, exabytes, even then, they still put this finbit functionality in the opcode of continuation frames to say, look, if you can't fit everything in one WebSocket frame, just send your message across multiple frames. You'll have a couple extra bytes of header overhead on your more than 16 exabyte message, but you can still do that with your finbit and opcode. So it's really future-proof. No matter how big your messages get, you can send them with WebSockets. Chrome, I have this on a slide in a little bit, but Chrome will, much before 16 exabytes, will start doing the finbit opcode thing and send a message over multiple frames, well before 16 exabytes. So maybe that is the preferred method, but for what it's worth, we can send up this 16 exabytes. It's such a crazy number over just the network. The amount of time it'd take to send that much information over a network would be absolutely outrageous. But you can send it in a single WebSocket frame. It's possible. It's physically possible, but not realistic. But the protocol will allow it. So to figure out your payload length when you're receiving a frame, you check your 7-bit payload length. If that value is exactly 126, read the next 2 bytes. Those next 2 bytes are your actual payload length. Else, if payload length, the 7-bit payload length is exactly 127, the next 8 bytes are your payload length. Else, that 7-bit payload length is your payload length. If it's anything other than 126 or 127, that's your payload length, and there's no more processing to do. So for Objective 2, for learning Objective 2, all the messages we test with will be in the 7-bit payload length range. The 126 and 127, that's when we're doing buffering. That'll be part of Learning Objective 3. Learning Objective 3 is handling large image uploads and handling large WebSocket frames. Both of those are going to require buffering. So for Learning Objective 2, it'll always be 7. So if you want to code it right away, go for it. But if you want to wait until you're doing Objective 3, until we have Friday's lecture and cover that content, you can assume that that's always going to be less than 126, and just use this as your payload length, and then go back later and code up Objective 3. It's up to you how you want to handle that. So that's payload length. That's probably where you're going to spend most of the time on parsing WebSocket frames, is getting your logic to handle that. Mostly because you have a sub-sequence in a byte array that you have to convert into a single integer value. That usually takes students a minute or two. A few Google searches, you'll find methods that do most of it for you. Or you can do what I intended, is appending all those bits together and doing binary math. But there's methods that really just do it for you. So I'll let you find those if you want. Or do it the fun way. It's up to you. I don't really have a preference on which way you do it. But all right. So, but I intended everyone would do it with a bunch of bit shifts, and I don't know. Almost nobody does that. Not when the methods exist. So the mask. Now we're finally at the masking key, which if the mask bit is 0, this doesn't exist. Remember. So that's only on the frames you send, though. When you receive a frame, mask bit will be 1. It will be 1 every single time. If you just assume hard-code it in your code, mask bit's going to be 1, I'm not checking it, because I don't want to write another bit mask and all that stuff. I ain't going to get mad at you at all. Just assume that this mask bit is 1 on messages you receive, on frames you receive. So that means these 4 bytes after all the payload length, whether it was a 7-bit, a 16-bit, or a 64-bit payload length. After payload length is going to be your masking key when you're receiving a frame. 4 bytes of masking key. And this, I don't think I put it in the slides here. I put it in the previous lecture slides. So just a reminder, the reason we're masking, the reason we have a random value in here is to bust up caching. We don't want anything caching these things. When a browser is sending a message to us, no matter how much aggressive caching we have as intermediate services, we don't want any of them caching these WebSocket frames. We want to get these messages on our server. Don't want it to be cached. So when we get the masking key, this is a random value, and then every 4 bytes of our payload is masked by having it XORed with this key. So we got some more bitwise operations here. So this is a randomly generated key, and then each 4 bytes, so the first 4 bytes of the payload data are XORed with this masking key. The next 4 bytes of the payload data are XORed with the masking key, next 4, etc. When you're doing this in code, what you'll have to do, so each 4 bytes are XORed with the masking key. What you'll have to do is read those 4 bytes and XOR them again with the masking key, which will effectively undo the XOR and get you back to the original message that was sent. So your task is to go through the payload and XOR it with this masking key. And what I recommend, because if you're trying to actually do this 4 bytes at a time, you're 75% of the time going to run into that index out of bounds error because you're trying to read 4 bytes, but the payload length wasn't a multiple of 4. You have to handle that in some way. If you're just taking chunks of 4, you'll get it 75% of the time. What I recommend in your code is not doing that at all. And instead, going through your payload, once you have your payload extracted, go through your payload 1 byte at a time and XOR 1 single byte at a time. And for each byte of payload data, ask yourself, which byte of the masking key does this need to be XORed with? So I'm going to read this byte. I'm going to take its index modulo 4, and that's going to tell me which byte of the masking key it needs to be XORed with. So 0, 0, 1, 1, 2, 2, 3, 3. When I get up to 4, modulo 4 is going to give me 0, and it says this one needs to be XORed with the 0th byte, the byte at index 0 of the masking key. Then 5 is going to XOR 4, give me 1, index 1, so on and so forth. And then you go through every byte of your payload data, XOR it with the correct bit or byte from your masking key, then you don't have to worry about index out of bounds. You just iterate over all the indices of your payload, grab the value at that indice, grab the bit mask at that indice, modulo 4, and that'll give you what you need to XOR. So that's what I recommend. It gets rid of the index out of bounds errors in a nice, clean way. So as an example, if your message is this is what's being sent in your WebSocket frame as your first 4 bytes of your message, and the client randomly generates a mask, a masking key of this, then what they're going to send, what's actually going to be in the payload of that data, is this XORed with this. So 0 XOR 0, 0, 1 XOR 1, 1, 0 XOR 1, 1, etc., and give us this. And then we're going to get this. This is what's in your payload, and you're given the mask. So we take this and XOR it with the mask again, and we'll get exactly back to the original message. 0 and 0, 0, 1, 0 is 1, 1, 1 is 0. All the XORs, all the math works out. It's effectively the message XORed with the mask, XORed with the mask. Well, the mask XORed with itself is going to be straight zeros, and this XORed with zeros is going to be itself. So we're XORing it with the same value twice. We get back to the original message. XOR is a very fast operation, so again, we're efficient. We're near optimal with this, and any bitwise operator is extremely efficient. Our processors know how to do bitwise operations, and we trick them into doing arithmetic. But if we're doing bitwise operations, extremely fast. It's usually each byte is just sending one operation to the CPU, roughly. I'm sure there's some overhead somewhere in there, but very efficient. And once you XORed the masking key with your payload, unmasked the data, then you have the message. At that point, you're done with WebSockets. Process the message however you need to do. Add it to your database, escape HTML, all the regular stuff. Attach the username to that message, all the stuff that we already did in homework 2. And then you go back to WebSockets. You have to create a frame. Create a frame using the same exact format and broadcast that message to all users. So you go to all your WebSocket connections, all your TCP connections, generate this frame and zap it to every single one of them, have a server-side push to every user. To do that, we're following the same exact format. So most of these are going to be the same. Opcode should be 1 for text. Fin bits 1, reserve bits are 0. The mask is going to be 0, is going to be a big change. The mask is 0, the masking key doesn't exist, and your payload is unmasked. We don't mask the payload here. And then payload length, you'll have to compute either 7 bits, 16 bits, or 64 bits. For objective 2, it's always going to be a 7-bit payload length. For objective 3, it can be any of the 3 cases. And keep in mind that your payload length is changing. Some students like to try to grab the bits from the frame that they received and reuse that as a payload length. Remember, your payload length is changing because you're adding the username into that JSON string and you're escaping HTML. It's changing, and by an unknown length. You can't hard code this in any way. So you do actually have to compute the new payload length and figure out how to get it into one of these 3 situations. Then convert it all to bytes, same way you did before, especially for the payload data. It's dot encode. You're sending a string, dot encode, and append it to the end. But getting all these bits exactly the way you want them will take a little bit more work, especially the payload length. You don't have to worry about the masking key. The first byte, for example, is always going to be the same exact thing. It's 10000001 or 129. First byte's always 129 every single time you're sending a frame. And then the mask bit 0, and then payload length, that's where you have to do some work, and then append payload data to the end. So payload length is the one big thing you have to compute when sending a frame. And why don't we mask when we're sending frames to the client? We're not concerned about caching. Why would a client be caching messages that we're sending to them? Just doesn't make sense. We cache to reduce load on our server. So the caching system can return a response faster without chewing up some CPU, or if it contains database lookups and stuff. We don't want to recompute things over and over. So we cache them so we can send the response faster. If the user's using our service, presumably it's because they want the information. They don't already have the information. It just doesn't make sense for it to be cached the other way around. We're always going to send them the response. No cacher is going to say, I know you want to send this to the user, but I think they already got this message. No, it doesn't make sense. Cacher's not going to do that. The only thing that's remotely like that is when you send a request and the cacher on the server side says, you already have the latest version of that thing, we're not going to resend it. So that's kind of client-side caching, but not really. It's still the server refusing to send something back. If the server decides it's going to send something back, it's going to get there to the client. So no concern. So we don't mask frames that are going back to the client. Okay. And again, assumptions, reserve bits are always 0. The opcode will not be continuation frame. I left it in the slide because I might bring that back next semester. But either text or closing the connection. I think we did get through these slides. Holy crap. Oh, we do got a few more. So we want to go through these. Just repeating things that I already said. I'll talk about this slide. So this is again, we're not doing this. We're not requiring this semester. But you might see this in your testing. Chrome, once you go, or any Chromium browser, when you go over 131,000 bytes in your message, Chrome will start splitting it into multiple frames. So don't test over 131,000, or else you're going to have to add more features to your server to handle this. Because we do need to go over 64K, which is, about half of this, right? We're going to get close to that. So don't go like more than double what you need to for your assignment. Make sure you don't go above this. Or if you are, test in Firefox. Firefox doesn't do the same thing. So just be aware of this. Then the fin bit is going to be 0 until the last frame. And the first frame will have the opcode, whether it's, because in general you want to know if it's text or binary data. So the opcode for the first frame will have the actual opcode, and then all the other frames will be zeroed out opcode for a continuation frame. And only the first frame will contain the payload length. The others will just have the payload. Wait, no. I'm like, wait, that doesn't sound right. No, the payload length is the length only for that frame. Then you have to piece them together. Oh, man, I said that way wrong. As I was saying, I'm like, is that really how it works? No, it doesn't. That's why it feels weird. The payload length is only the length of that single frame. So when you get the first frame, you have no idea how large the entire message is or how many frames it's going to be. You just have to read each frame until you see a fin bit of 1. Then you know the end. Or don't worry about it. This semester, we can just not worry about it. Okay, and we did make it to the end. And the music's not going to kick in, but we're good. The opcode. I think the API just hates me right now. The opcode field defines